Okay, so we are going to finish up chapter 29 and then we're going to do some review. Some of the last material in chapter 29 is not actually on the test. I'll try to kind of go over what things you might really want to study as you prepare, but we do need to finish it up. So we were discussing displacement current, and Maxwell gave us this definition of displacement current that said the displacement current is epsilon times change in the electric flux per unit time. And that made a change to Ampere's law. Ampere's law now, it used to look like this. The line integral of B dot dl was mu naught times the enclosed charge. But now instead of just an enclosed charge, we have the conduction current plus the displacement current. Now, what you want to remember is if you're outside the capacitor, the displacement current is 0. If you're inside the capacitor or between the plates, that means the conduction current is 0. So this is outside, I said the capacitor, but outside the plates. So the bottom line is you have one or you have the other, and they're actually equal. So you're either going to have this when you're outside of the plates, or you have this when they're inside of the plates, and they are equal to the exactly same amount. So this is just an adjustment to Ampere's law when we're looking at a capacitor. There's no capacitors involved. What we've been doing, which is just mu naught times the enclosed charge, which would be this, it's going to work perfectly. Okay. Last thing in this chapter is just summarizing Maxwell's equations. Maxwell's equations do for electromagnetism what Newton's laws do for motion. But the big difference is that Newton's laws can be understood at a pretty simple level. We can kind of understand those in middle school. Maxwell's equations really require calculus. So I'm going to write those down for you. Let me find an eraser. And you'll see they have a certain amount of symmetry. You'll also see that they weren't really developed by Maxwell. He just pulled it all together. Maxwell's equations. Our first one is Gauss's law. For electric fields. And that was the closed interval of E dot dA, so we're going way back earlier in the semester, is equal to the enclosed charge over epsilon naught. You'll recall that that also was equal to, and it's not part of the law, but that equaled the electric flux. So that's our first one. Also have Gauss's law for a magnetic field. And it said that if you have a closed interval over a surface, B dot dA, it equals 0. That's also the flux. The magnetic flux through a closed surface is going to always equal 0 because the amount of flux into the surface and the amount of flux out of the surface will have to equal 0. Okay? So very similar looking. One says it's the enclosed charge over epsilon naught. If you're looking at magnetic flux, the magnetic flux for a closed surface is 0. This would be the magnetic flux, but that magnetic flux would be 0. Our third one is Faraday's law. And this is specifically for stationary integration path. But it's what we learned first, and that is that the integral, this is a line integral of an electric field E dot dl. You can tell it's a line integral because we're integrating over a line. So this would be a closed linear path, whereas this was a closed surface. Faraday's law says that is equal to the change in magnetic flux per unit time. You can also think that that's going to be your induced EMF, right? This isn't really part of the law, but that's what we know. The change in your magnetic flux. And finally, we have Ampere's law. Again, for a stationary integration path. We're not having a moving conductor here. And that says the integral of B dot dl, again, that's a line integral, is simply equal to mu naught times the conduction current or the displacement current. You'll either have this or you'll have this. You really won't ever have both. You can see all of the symmetry. I'm going to take this part off. That's not really part of the laws. Ampere's law is incredibly similar looking to Gauss's law. But then Gauss's law for electricity and magnetism, also very similar looking, except we know there's the flux through a surface here can be a positive or a negative number. The flux through a surface, when you're talking magnetic flux, is going to be 0. Those 4 laws is where pretty much everything else in electromagnetism comes from. If you continue to study physics, I know most of you want to be engineers, and you might not want to be electrical engineers. This might be the last time you have to deal with them, or you might take whole classes that deal with them. All right, with the remaining time, I want to review. I'm worried you've got a big test on Monday. David's been out of town, so let's try and get some review done. I want to start with chapter 27. I know that I've told you that this test does not have any multiple choice. This is strictly a problem-solving test. You'll have your formula chart like always. You'll have the formulas that you need if you can decide what it is you need to do and how to tackle the problems. That's what I'm going to try to help you with. So in chapter 27, we deal with magnetism for the first time, and we start off by simply looking at magnetic forces. What happens in a magnetic field? What kind of forces do we feel? We also spend some time talking about magnetic lines of flux and flux. I think I'm going to work that in as we go. So I'm going to start with, let's see. idea of a magnetic force on a charged particle. I think that's the right place to begin. If you have a charged particle and it's in a magnetic field, then it's going to feel a force of QV cross B. I think that's all I need there. That's it. We'll talk about the right-hand rules. If I want to get the direction of V cross B, I point my fingers with V and I curl them towards B, and my thumb gives me the direction of force on a positive charge. If the problem has a negative charge, I do the same thing, and then when I find the direction with my thumb, whatever it is, I simply reverse it. So I thought we would start by just looking at problem 5 in the back of the chapter. So if I go to problem 5, and I just tried to pick some problems you haven't already done, there would be help in just reviewing problems you have already done, because those were picked out because they're good problems. Problem 27.5 says we have an electron moving in the xy plane. If at time t a magnetic field B, okay, so what they're telling me, this is number 5. First they're telling me I have an electron, which means I have Q. And they also tell me that I have a magnetic field. And that magnetic field is 7.40 times 10 to the negative 2. That's Tesla, that's coulombs. What about direction? Oops, I looked at the wrong problem. I'm sorry. I don't want to mix my problems. Let's get the right B. And problem 5B is 0.2 Tesla. And the direction is the positive Z. So if we were doing IJK, it'd be in the unit vector would be K. Okay. If at a time t the field is 0.2 and the positive Z exerts a force on the electron equal to F equal 5.50 times 10 to the negative 18 newtons, the direction of the force is in the negative Y. It says, what is the velocity, magnitude, and direction of the electron at this instant? Okay, so we've got this situation. It tells us that we've got X, Y, Z is out of the board. B points this way. It's along the x-axis. I'm just trying to get a feel for what's going on. There's my B. The force that it feels is down. So my force vector is in the negative Y. And all it tells me about the velocity is that the velocity is in the xy plane. See if we can think this through. If the force is a positive charge would be up, then V cross B VB is out of the board, so almost seems like it could be moving in the negative x direction, it was moving in the negative x direction and you were positive, when you curled it towards B, the force would be up. In this case, the force is down. So that's because it's a negative charge. So my gut feeling says that V must be in the negative x direction. All right, I think I have a direction. I haven't checked my answer yet. So let's go ahead and work the problem. The magnetic force, this magnitude would be Q, V, B, sine, I don't know what angle, phi or theta. But to me, I think this is 90 degrees. I think V cross B is 90, or it can be 90. They don't tell me anything differently. Let me check that. Okay, I think we're on it. I just checked. It said I was right with that whole negative x direction. So this will be sine 90, so that'll just be 1. And we can just fill in our numbers now. We've got 5.50 times 10 to the negative 18 has to equal 1.60 times 10 to the negative 19 times V times B. B is 0.2 Tesla. I'm going to need a calculator, obviously. When I solve for V, I'm going to have 5.50 times 10 to the negative 18 divided by charge of 1.60 times 10 to the negative 19. And then divide that by 0.2. And I'm getting 172 meters per second in the negative x direction. You could write that as negative 172. X is ijk, so it would be negative. That would give you a negative x direction, meters per second. Either one of those is perfectly fine. This one probably, top one's probably what comes a little more naturally. Do a quick check in the back, because I don't do any of them wrong. And that is the right magnitude, that is the right direction. So, first formula you should practice around with, rework these problems yourself, I'd say was that one. I know we used that one on the test. If I push forward a little bit, one of the other ideas that's really important is how these charged particles move when they enter magnetic fields. And we found out earlier that if the velocity is perpendicular to the magnetic field, then they will move in a circle, and that circle has a radius equal to the momentum of the particle over QB. I put Q in absolute value. Again, we'll treat all of the charges like they're positive, but then if they're negative, we'll just know that the force is in the opposite direction, and it will make a circle going in the opposite direction. I want to think about this before I work a problem. I can just think about, what if I have this magnetic field that goes right into the board? Now, if I have a charge, if I have a neutron, if I have a neutral particle and it comes in, here it is, it has no charge, and it's going this way. Something that has no charge is not affected by a magnetic field. It would just pass right on through. No problem. But if I change this from, say, a neutron to a proton, a positive charge, then I have to say, okay, there's my velocity. V cross V. V goes this way, cross V. This feels a force upward. And when it feels an upward force, it curves its path like this. Now, at this point, the velocity is this way. So now if I do the velocity V straight up, cross V, I see it feels curved back this way. And it will do this. Now, if it leaves the magnetic field, it will just continue in a straight direction. So if I run out of magnetic field, it's just going to make a half circle. And then it'll just go straight. If there's more magnetic field over here, depending on the situation, it might just keep going. Or if there's more magnetic field, it'll just keep moving in a circle. And this formula tells us. Now, if the particle was negative, it would not feel an upward force here. It would feel a downward force. And that would cause its circle or half circle, depending, to go this way. So a neutral charge would just remain undeflected. A positive charge feels an upward force, and then it continues to feel forces that make it move in circles. A negative charge feels this downward force, and it continues to move in circles. So let's look at a problem that uses this idea. All right, let's look at problem. I have problem 16 circled. So let's try problem 16. Problem 16 says an alpha particle, so number 16, got an alpha particle. An alpha particle is basically 2 protons plus 2 neutrons. So its charge is double that of an electron. So it has a charge of 3.2 times 10 to the negative 19 coulombs, and it's positive. It basically, if we need the mass, it has a mass that they give us 6.64 times 10 to the negative 27. It's basically the mass of 4 protons, because protons and neutrons have the same mass. So we've got 4 of those heavy particles, 2 protons, 2 neutrons. It's traveling horizontally at 35.6 kilometers per second. So it has this velocity, 35.6 kilometers per second. And it enters a uniform vertical 1.80 Tesla magnetic field. Okay. Okay. So the magnetic field B, 1.80 Tesla. And it basically says the magnetic field points up. You picture B being like this. And the particle's traveling horizontally, so it's coming along like this. If you look at it, at that particular moment, V cross V is going to be out of the board. Now, it won't remain traveling out of the board. It would travel in a circle as it was moving this way. Then if you do V cross V, if it curves out this way, what's coming this way now, then V cross V would look like this, and it would turn that way, and you would get a circle that would do like this. You probably can't picture it coming out, but it would make a circle. All right, let's see what they asked me to find. What is the diameter of the path followed by this alpha particle? Like, first off, they just want the diameter. Well, the diameter is just twice the radius. So the diameter is going to be 2 times the radius, so 2 mass times the velocity. 35.6 kilometers is 35,600 meters per second. The charge is 3.2 times 10 to the negative 19 coulombs, and B is 1.80. So the only thing different is I just multiplied by 2 because they asked me for a diameter. They did not ask me for the radius. So 2 times 6.64 times 10 to the negative 27 times 35,600 divided by 3.2 times 10 to the negative 19 divided by 1.80. And I get 8.21. I think I have 3 sig figs. I put a 0 here. So I'm getting 8.21 times 10 to the negative 4 meters. Or I change that to 0.821 millimeters if I wanted to. I'd leave it the first one, but I'm not sure what the back might have it in millimeters. Oh, the back doesn't have it at all because this is problem 16, so we're just going to trust me. B says, what effect does the magnetic field have on the speed of the particle? And the answer is absolutely none. Because the magnetic force is going to be perpendicular to the direction of the particle, it doesn't affect its speed, it only affects direction. Anytime you have a force that is perpendicular to the direction of the velocity, it doesn't speed up or slow down, it changes the direction of the velocity. It only causes acceleration. C says, what are the magnitude and direction of the acceleration of the alpha particle while it is in the magnetic field? What's the acceleration? Well, acceleration is simply equal to force divided by the mass. So what I really have to do to answer this question is say, well, what's the magnetic force? The magnetic force is QVB. We know everything's perpendicular, so V cross B angle will be 90. It's just QVB. If I multiply those values, well, let's just go ahead and get acceleration. So acceleration will be QVB divided by the mass. So I've got the 3.2 times 10 to the negative 19. I've got 35,600. B was 1.8. And the mass of that particle was at 6.64 times 10 to the negative 27. That's how I get my acceleration. Three point two times 10 to the negative 19 times 35,600 times 1.8 divided by 6.64 times 10 to the negative 27. And I get a huge acceleration, but that's very plausible. 3.09 times 10 to the 12th meters per second squared. That is an even problem. I don't have the answers in the back of the book, I will check them later in the solution manual, and if they're not right, if I made a mistake, I'll update you, but I feel like we did a good job. I'm not very worried. That was a pretty straightforward problem. Okay, so we've covered the magnetic force on a moving charge, QV cross B, and we've also looked at that circular motion when the velocity is perpendicular to the magnetic field. When that velocity is perpendicular to the magnetic field, that charge is going to move in a circle, and this formula is going to determine the radius of that circle. Cap all these markers I'm using. Okay, so what's the next idea we want to look at? Let's see. Have either 30 or possibly 33, and they both deal with a magnetic force on a wire. A magnetic force on a piece of wire. We go back to what it was for a charge. The force on a single charge was QV cross B. If I have a lot of moving charges that make a line, this is going to change to I, which is the current. Instead of a single charge, we have a lot of charge, L. Notice current is meters per second, and L is, current is amps. Say one more time. This is coulombs. This is meters per second. This is coulombs per second times meters. We still have the same units here. Cross B. If you want to get the magnitude and you don't care about the direction, that magnitude is going to be I, L, B, sine theta, where theta is that angle between L and B. If L is perpendicular to B, that gives us that 90-degree angle, and then sine theta is going to just equal 1. So this really looks pretty similar, but it's for a piece of wire. Again, you'll be really glad that you have a formula chart. You don't absolutely have to memorize all of this, but you really do need all of this to feel familiar. All right. I think I'm going to challenge myself, and let's do problem 33. And problem 33 is about a magnetic balance. And I like the idea of it because it has to do with kind of looking at gravitational forces and looking at magnetic forces. They give me a problem where I have a battery and a resistor. So, and they draw the battery. There's the battery. There's a 5-ohm resistor. Down here we've got, let's see if I can draw this the way they did. We've got like just a metal rod here. It's actually separate. It can come loose. So here's this metal rod here. Surrounding that metal rod, we've got a magnetic field that points directly into our board. So this is problem number 33. So you need to look in the back of your book to find this problem. Here's our magnetic field. And this bar can be used to weigh something, to find something's mass. So we have some little arbitrary mass that's hanging down here. Pull that down. I want to read the problem now so we're sure we're all looking at the same things. It says the circuit shown is used to make a magnetic balance to weigh objects. The mass M to be measured is hung from the center of the bar that is in a uniform magnetic field of 1.50 Tesla directed into the plane of the figure. So our B is 1.20. No, 1.20, 1.50. Our B is 1.50 Tesla. The battery voltage can be adjusted to vary the current in the circuit. The horizontal bar is 60 centimeters long and is made of extremely lightweight material. It is connected to the battery by thin vertical wires that can support no appreciable tension. All the weight of the suspended mass is supported by the magnetic force on the bar. We've got a situation where they've just basically said, look, this bar is weightless. That's nice. It said these wires cannot stand any tension at all. If there's any tension in the wires, this thing will drop. So what we have to do, if we think about a free body diagram, is we need the magnetic force upward on this bar to be balanced by the gravitational force. Really what we're trying to do is balance the weight by a magnetic force. I'm going to need a magnetic force to point up because I know the weight, which is mg, is going to point down. Let's look at the direction for a minute. This is my rod. B is into the board. I need a force that goes up. I need the charges to go this way, so that when I put my fingers this way, I curl into the board, the force is up. So I can tell I need my current, my positive current, to go this way. I need this to be positive. I need this to be negative. That's going to give me a current that's going to give me this upward magnetic force. That magnetic force is going to be equal to ILB, because IL cross B, and I is perpendicular to B. I need ILB to equal mg. That's how I can balance things. Let's read some more. Which point A or B should be the positive terminal of the battery? Well, the way they've drawn it, this is A and this is B. So I've already said A needs to be positive, because if A is positive, my current is going in the direction that gives the magnetic force to be up. So I have an upward force on this rod right here. I also have a downward force on this rod. One's magnetic, one's gravitational. If the maximum terminal voltage of the battery is 175 volts, what is the greatest mass that this instrument can measure? So when I turn up the voltage, the greatest voltage I can get is 175. Well, V equals IR. So I'm getting a maximum current. This is a maximum voltage of 175 volts divided by 5 ohms. My maximum current, 175 divided by 5, is 35 amps. I can get a current of 35 amps. Using that maximum current, I can figure out how big this can be. What's the greatest possible mass it can handle? So I is 35. The length they told me in the problem, I didn't write it on the picture, but let's read it. The horizontal bar is 60 centimeters. So my length here from here to here, 60 centimeters or 0.6 meters. The magnetic field strength was 1.5 Tesla. That equal M times 9.80. So that's how we're going to try to suspend. If they had given that bar some mass, this would have just been the total mass of the two, but they didn't. So we can just get this. It wouldn't have been much more difficult. We would have just found the total mass and then subtracted the bar. So 35 times 0.6 times 1.5 and divide by 9.80, and that's 3.21 kilograms. That's actually pretty big. Of course, that is a large current, and that's a strong magnetic field. So we've got some pretty big numbers in there. We've got 35 amps. All right, let's see if we were right. This is problem 33, and the correct answer is 3.21 kilograms. We are on a roll. Okay, I want to leave chapter 27. I feel like we've done, those are the points that I feel like are really important. What's the force on a particle moving? What's the radius of that motion if it's moving where it's perpendicular to the magnetic field? And finally, what's it look like if instead of a single charge, we actually have a current? So that would be my highlights of chapter 27 that might help you do well on this exam. We only have, oh my goodness, only have 30 minutes left, so I probably need to pick up my pace a little. But I think getting the foundation right is important. So let's move on to chapter 28. Let me go ahead and write this down. I had kind of made some notes of helpful problems. So if you're getting ready to study, here are my helpful problems. Chapter 27, I had 5, 16, maybe 30, 33. Just good problems to practice. For chapter 28, I have 21, 29, and 43. And for chapter 29, I had looked at 1, 5, and 27. Obviously, I'm not going to have time to work another 6 problems. I've only worked 3. So let's at least work 1 out of each chapter. Let's look at chapter 28. Chapter 28 goes into looking at magnetic fields that are caused by different things. What's the magnetic field of a point charge look like? What's the magnetic field of a line segment look like? What's the magnetic field inside a solenoid? All kinds of magnetic fields. I would say, we look at kind of the summary. There was a lot in this chapter. If we had a moving point charge, for a point charge, we had something like mu, that the magnetic field was mu naught over 4 pi, and then QV cross R, but R is just a little unit vector over R squared. If instead of a point charge we go to a line, like a wire, if we look at an infinitesimal part of it for a conductor. It's mu naught 4 pi I dl cross r. Again, that's that unit vector over r squared. However, if that's just a straight wire, that's just a piece of straight wire, that's going to look like mu naught L, where that's the length of the wire. IL, sorry, I left out the I. Mu naught IL over 4 pi r squared. That's what you're going to get. And that's over there. Well, I don't see it over there. I thought it was going to be on our list of different things. I don't actually see it. That's okay. There is a list on the formula chart of some different magnetic fields. Oh, no, I'm off on the long straight wire. If we do it per unit length, and I think I did have a mistake there, we get something like B equals mu naught I over 2 pi r. That's what I meant. This is for a long straight wire. And that one is on the formula chart, I'm pretty sure. Yes, it's the very first one. All right, let's just work a problem. I have to say, I think those are probably the most important, but there's some others, so pay attention to any of them. I'm going to look at 21, 29, and 43 and pick one that I think will be really helpful. You should do the others. So what's 43? 43 is okay, but let's look. 29. 29 looks good. Let's look at 21. Let me look at the text. Okay, 21, direction of the magnetic field. Let's look at 21. I like 21. You could go back later and perhaps do 28 and do the other one, 43, but let's look at 21 with the time we've got. Okay, well, we can erase all this. You've got this written down. So this is chapter 28. And this is number 21. Problem 21 says, two long, straight, parallel wires 10 centimeters apart carry equal 4 amp currents in the same direction as shown. Find the magnitude and direction of the magnetic field, and then it gives us some various different locations. So I'm going to draw the picture they drew. Two wires, they both are coming out of the board, so they have one coming out of the board, another one coming out of the board. They both carry 4 amps. They are 10 centimeters apart from here to here. Okay. I1 equals I2 equals 4 amps. All right. The first question it says, part A, what is the magnetic field at point B, midway between the wires? So they want the magnetic field right here. All right, let's use our right-hand rule. If I use my right-hand rule, and I have my thumb with the current, and I rotate, that gives me the direction of the magnetic field. Remember, magnetic fields look like circles around this wire. So it would be a circle that goes this way. Well, at this point, it'd be a circle like this. So right here, I know B1 points straight up. The magnetic field due to that wire points straight up. This other wire, if I put my thumb out of the board, its magnetic field lines go the opposite direction. So its magnetic field lines do like this. They go this way. Actually, they go the same direction as here and here. They both go counterclockwise. But when I'm out here, if I'm going counterclockwise, I can see that that makes B2 point straight down. So B1 is pointing straight up here. B2 is pointing straight down. They have to have the same magnitude because they have the same current. So I'm going to say the answer to part A is going to be 0. And that's exactly what the book says. So we're batting 1,000 today. I'm so glad. The second part, question B. Question B says, find it at point 2, which is 25 centimeters to the right of P1. Okay. P1 is midway and P2 is 25 centimeters to the right. So this was, we're going to erase all of this. We've got all this drama, but we got 0. This is P1. And this is 5 centimeters and this is 5 centimeters because it's at the midway point. P2, it said, was 25 centimeters to the right of P1. So if I go 25 centimeters to the right of P1, I'm coming out here. This is P2. From here to here would be 20 centimeters. These two are 25 centimeters apart, P1 and P2. They want me to find the magnetic field there. That one's not going to be 0. So what we need to do is we need to think about, and we don't really need P1 for this, it was just to help us draw the picture. The magnetic field lines are still counterclockwise. So if this is counterclockwise, I know that B1 is up. It's going to be weaker than B2 because it's farther away. It's 30 centimeters away. Okay. B2, if we're going counterclockwise, they both go up. When I draw my counterclockwise circle for B1, it's going up. When I draw it for B2, it's going up and it's even bigger. So I've got B1 and I've got B2. They're both going up because they're both doing these counterclockwise circles. I just have to calculate them and add them together because they were nice enough to go in the same direction. In both cases, we're looking at a point to the right of the wire. Here that didn't work. This point was right of the wire, but this point was left of that wire and they canceled out. Okay, so what's our formula for the magnetic field due to a wire? For a long straight wire, it's just mu naught I over 2 pi r. So I'm just going to add the two together. For B1, it's going to be mu naught, which is 4 pi times 10 to the negative 7, times I, which is a current of 4, over 2 pi r. And for B1, r is 30 centimeters. 5 plus 5 plus 1, so 0.30 meters. Plus, looks exactly the same, mu naught times 4 times 2 pi, but the second wire is only 20 centimeters away, so 2, 0. I just have to add those together. Pull out of our calculator. So 4 pi times 10 to the negative 7. Oh, let's simplify a little bit. The 2 pi's go away, and that's just a 2. Okay. Now we'll say, oh gosh, this is actually pretty easy. So that's going to be 2 times 4, 8 times 10 to the negative 7 divided by 0.30 plus, I'm going to have 8 times 10 to the negative 7 divided by 0.20. That gives me a total magnetic field of 6.67 times 10 to the negative 6 Teslas. I really have to find the directions of those magnetic fields first so that I'm certain whether I'm going to be adding them or whether I'm going to be subtracting them. And that is the correct answer. I don't think we'll do part C, but part C is the same thing, only now 0.3 is 20 centimeters directly above P1. So we're going to do it, we would be doing a point here. If I did a point up here, I would have to do some math to find this distance, but I could certainly do that. It would not be that difficult. Let's see, I might have time for 2 more problems. I'm going to just try and pick which problems seem like the ones we need to be looking at. It's always kind of a challenge. I think I really want to move on into chapter 29 and look at this idea of magnetic induction. Magnetic induction involves finding changes in flux. Now, when you're studying chapter 29, you can probably concentrate your efforts on the first part of the chapter. I would say section 1, which is on flux. We didn't even really have problems, but you need to understand magnetic flux. But section 2 on Faraday's law, and section 3 on Lenz's law, and section 4 on motional EMF. You do not have to worry about induced electric fields or displacement currents or Maxwell's equations. I wanted you to see all of that. But what you really need to understand is, do I understand Faraday's law? Do I understand Lenz's law? Do I understand motional EMF? I think those 3 pieces are going to save you in this chapter. Let's see. I've got problem 1, 5, and 27. 27 is a motional EMF. Now, we might do that one, but let's start with either 1 or 5. Okay, I think we'll do 5. We'll do 5. So we're looking chapter 29. Number 5. A circular loop of wire with a radius of 12 centimeters and oriented in the horizontal XY plane is located in a region of uniform magnetic field. A field of 1.5 Tesla is directed along the positive z-axis. So, there's x, there's y. They said horizontal. I'm not going to draw it horizontal. I'm going to draw it this way. And there's z. I might need to draw it horizontal to answer the direction question. We'll see. Yeah, I will, because they tell me to look at it from above. If we lay this back where x, y is horizontal, then looking on it from above is looking on it from the positive z-axis. So we'll be able to do that. A circular loop of wire, radius 12 centimeters, okay, is located in a region of uniform magnetic field. Okay. So, there's our loop with a 12 centimeter radius. Our magnetic field is along the z-axis. And it's 1.5 Tesla. Like I said, I really didn't draw it the way they said to. Let me go and just draw it the way they said. So you'll have two pictures of it. If we draw this in the horizontal XY plane, it looks like X is this way, Y is back this way. I've just laid it over flat, and Z is straight up. I just took this picture and tilted it. They're saying that this circle that we're looking at is in this XZ plane, and we've got a 1.5 Tesla straight up magnetic field. All right, what do they want me to do with it? It says, if the loop is removed from the field region in a time of 2 milliseconds, find the average EMF that's induced in the wire. So we're going to remove it really quickly in 2.0 milliseconds. Really, it's a delta T. What we have to do is find the flux before and after it's moved. So, because we're going to be looking for a change in flux. Our average induced EMF, change in flux, change in time. We put a negative there. How much flux do we have to begin with? Flux is the magnetic field times the area times, I believe it's cosine theta, but we don't have an angle. Everything's perpendicular. So we are fine. The area vector, if you'll remember, this is a dot product. The area is perpendicular, so our area vector points straight up, perpendicular to the circle, just like the magnetic field. So that means its angle 0. Cosine 0 is just 1. So our flux is just B times A. And you can see it by looking. All of the flux is going through the circle. So I've got 1.5 Tesla times pi r squared. And r is 0.12 meters. We've got to work in meters. So my flux, just my magnetic field times my area, 1.5 times pi r squared is 0.0679. It's 0.06786. I'll just leave an extra digit. That's how much flux. That's Weber's. I have at the beginning. My induced EMF is my change in flux. So if I do a negative change in flux, well, that's going to be 0 minus 0.06786. In other words, then my change in flux is negative because I went from this to when I do final minus initial. But I have a negative of a negative. The time was just 2 milliseconds. So my average EMF actually comes out to be positive, And I just need to divide that by 2 times 10 to the negative 3. I get 33.9 volts. And I'd have to look at the problem to see whether I have 2 significant digits or 3. I always do that last. So when I look at that problem, I am seeing mostly 2 sig figs, so I will write that answer as 34 volts. That's the average induced EMF. Very briefly, we've got some pretty serious voltage going on. And that is the right answer. The other thing it does ask is if you are viewing this situation from above, what is the direction of the induced EMF? Viewing it from above is also like looking at it this way, because it's looking at it from the z-axis. Lenz's law, what's going on? Z is pointing up, but it's going down. It's getting smaller. So our change is this way. That means our induced magnetic field will be up. I want an induced magnetic field in the same direction as the original field. If the original magnetic field gets smaller, then the new induced field will be in the same direction because it'll try to short back up to its original. So that means it does this. Or if it's coming straight out of the board, so viewed from above, it's going to be counterclockwise when you view it from above, if you view it from that z-axis. All right. I have 7 minutes left. I think I'll do one more problem, and then you will have seen a lot of physics problems today. I hope it helps you study. One of the ways you prepare is just to do lots of problems. And I've kind of tried to give you some guidance on which type of problems seem important. So let's look at number 43. I believe that's chapter time. I believe that's the one I had. Let's see. Yeah, no, that's chapter 28. Number 27. Okay. Number 27 says, it's an emotional EMF problem. The conducting rod AB, shown in the figure, makes contact with metal rails CA and DB. Oh, I see, they've got everything labeled. The apparatus is in a uniform magnetic field of 0.8 Tesla, perpendicular to the plane. Find the magnitude of the induced EMF in the rod when it's moving toward the right with a speed of 7.50 meters per second. So we are going to draw the picture and label everything and get going. So there is the conducting rails. And here is this rod sitting on top of it, ready to move. They tell us that the distance between the rails is 50 centimeters. This is A, B. This corner is C. This corner is D. It's moving to the right with a velocity V, which is 7.5 meters per second. Okay, I think I have everything. Oh, uniform magnetic field that points directly into the board is 0.8 Tesla. So 0.8 Tesla right into the board. Okay. We are ready to solve. Find the magnitude of the EMF induced in the rod when it is moving to the right with a speed. Okay, that is our classic moving the rod, motional EMF. The induced EMF is VBL. Pretty sure that's on a formula chart somewhere for a rod. V is 7.5 meters per second. B is 0.8. And L is 0.5. So we need to get that magnitude. 7.5 times 0.8 times 0.5. That is 3. That came out nice. So we have an induced EMF of 3 volts. In what direction does the current flow in the rod? Well, if you think about it, there's a couple of ways you can think about it. You can think about it with Lenz's law. If the rod is moving that way, the magnetic field points into the board and the flux is increasing. So if it's into the board and getting bigger, we would have it out. And out would mean counterclockwise. That is one way to look at it. That's actually not how I thought of it first, but that's what Lenz's law will say. The other way is to say, hey, look, this thing is full of charges, and those charges are moving to the right. The magnetic field is in, so all of those positive charges feeling upward force. And that gives you the exact same result. So it's 3 volts, and it's counterclockwise. If the resistance of the circuit A, B, D, C is 1.5 ohms, assume it's constant, find the force, the magnitude and direction required to keep the rod moving to the right with a constant speed of 7.5 meters per second. You can ignore friction. So they're telling us we have 1.5 ohms of resistance. Well, current is voltage over resistance. 3 over 1.5 is 2 amps. So we've got 2 amps of current flowing through this. Next question, part of the question. What's the force required to keep the rod moving to the right with a constant speed? Okay. If I want to keep it moving to the right at a constant speed, I need a force that way. The magnetic force on that current, if I go back to magnetic forces, remember, if I have a wire, it's going to have a magnetic force that's IL cross B, which is going to look like this. It's going to have a magnetic force this way. This is going to be my applied. This is how hard I'm pulling it. If I want to move at a constant speed, going all the way back to my early understanding of Newton's laws, if I want to move at a constant speed, I want my net force to be 0. I want the applied force to equal the magnetic force. And the magnetic force is IL cross B, or ILB, so 2 amps, 0.5 meters long. B is 0.8 Tesla. 2 times 0.5 times 0.8. And that, well, yeah, that's 0.8. 2 times 0.5 is 1. I'm getting 0.8 newtons for what my applied force. I'm going to have to pull it to the right with 0.8 newtons of force to counteract that magnetic pull. Double check that one. That's right, we've got it correctly. And then finally, they have one more question. It says, compare the rate at which mechanical work is done by the force FB with the rate thermal energy is developing the circuit I squared R. So, they want me to compare the power FB, which is for the rod. That would be 0.800 times 7.5 meters per second. So 0.8 times 7.5 is exactly 6 watts. That's the mechanical power. That's what you're doing when you pull it. The power generated in this circuit is I squared R. That is 2 amps squared times 1.5. That's 4 times 1. That is exactly 6 watts. That makes perfect sense. You're doing work on it at a rate of 6 joules per second, and we've idealized everything. So the power